Where were we? So I wanted to show you the map between SU2 and SO3. I think that is where we stopped, right? Yeah, this is, it's not only, of course, this is itself a very interesting issue here, because you have two groups, SU2 and SO3, which are each three-dimensional, right? Of course, in general, dimension is the same, doesn't necessarily mean the groups are the same, or related to each other in some simple way, right? But in this particular case, it happens they are related in a very simple way. So the purpose of this thing is to show the precise relation between SU2 and SO3. But there's also another important reason to do this, and I will just mention this now. Okay. First of all, there is a, we briefly talked about the representation. I mean, I didn't say it in detail last time, but just briefly we mentioned that. So if I have some Lie algebra, let's say some, what I was calling, the symbol we were using for Lie algebra elements was what? I don't remember. Was I calling T or something? I don't know. So let's say so there is a Lie algebra. And it's, let's say the generators are, I call the generators, so call the generators. Give some name to that. So T1, T2, and let's suppose the dimension is D. The dimension of the Lie algebra is D. Then I have D independent generators. And of course, the full Lie algebra is the vector space generated by these D generators, which carry also another additional information, which is the commutator, the Lie algebra, right? It is not just a vector space, it has more structure. So it's more rich than the vector space, right? It has also Lie algebra. So this was it. And of course, there is also the corresponding Lie group, which will be some group G, let's say. This was the Lie algebra, we were calling this calligraphic G. So this is also same dimensional, D-dimensional. And what it means is that if I want to describe this G, then I can have D independent parameters, right? Just like here, for the SU2 we had 3 parameters, right? Same way for this D-dimensional Lie group, so we'll have D parameters. Now, what does it mean, representation? It means you map say the Lie algebra G, and the same thing, the same statement is also for the Lie group G, to the space of say n by n matrices. Okay. Now, what kind of a map is it? First of all, the important point is that this should be linear map for the Lie algebra. It's a linear map. That is, I mean, for the group you cannot talk about linear map, because in the group there is no linear structure, no. But in here G is a vector space. This Lie algebra is a vector space, so there is a vector space structure, right? So what the statement is that this map should be linear. What it means linear? So suppose I have X and Y belong to G. Okay, and let's suppose the map I write this map as R. Okay, R is just a symbol. This is a map. But what does it mean, this map? That this R acting on X is some n by n matrix. Let's call it MX. Or, okay, I don't have to. Okay, this itself is an n cross n matrix. Okay. This is a symbol, R of X. So R takes X, R is a map from X to n by n matrix. Okay. Similarly, R of Y is going to be another n by n matrix. In general, another. It could happen, it's the same, it doesn't, I mean, generally it will be different, because X and Y are in general different. I'm taking X and Y to be different elements. Okay. So linearity just simply means that R times, say, AX plus BY, where A and B are some numbers, real numbers, let's say, okay? The real or complex depends on whether the Lie algebra is real or complex Lie algebra. Let us focus for the moment on the real. Right? But the same discussion goes through for complex also. So let's suppose A and B are real numbers. So AX plus BY is also an element of Lie algebra, right? Because Lie algebra comes with a vector space structure. Okay. Now the statement is that this guy is the same as A R of X plus B R of Y. This is a statement. Okay, for the linearity. Okay. You see that what we are using? We are using the vector space structure of the original Lie algebra, and here we are using the vector space structure of the matrices. Because matrices, you know how to multiply by a number and how to add the two matrices. So that itself is a vector space, right? So what we are saying is that the map is compatible with the vector space structure of the Lie algebra and the vector space structure of the matrices. Okay? That is what it means here. Now, at the level of group, exactly the same discussion you can carry out. But of course, now there is not a linearity is not there. Because group has no linear structure. However, you still have, let's suppose G and H, two elements, belong to capital G. Okay? So these are group elements now. So again, we have a map. G goes to some matrix, n by n matrix, and H goes to an n by n matrix H. Okay. Now, in the group, I have a composition rule, G times H. This is going to be some element in the group. Okay. Now, you ask the question, of course, if I give you this map, then this also is mapped to some R of G H. Right? This is just a map. So G is mapped to RG, H is mapped to RH, and this G times H, which is some element of the big group G, it's also going to be mapped to some matrix. Okay? But now the statement is that there is a relation between these three. And the relation is that this object is nothing else but RG times RH, where this times is simple matrix multiplication rules. So this is just by matrix multiplication rules. I mean, if I just give you some map, it need not satisfy this condition, right? But this condition is the most important thing here, because this condition is saying that the composition rule in this group is compatible. I mean, the map is such that this composition rule goes over to the matrix multiplication rule, right? This map is such that's the most important part. That it should be compatible. So you have a structure in districts, which is the composition. You have a structure in the n cross n matrix, space of n cross n matrices, right? This structure should go over to a structure in the matrix.
If this condition is satisfied for Lie algebra, that condition is also satisfied for the
Yeah, correct. Yeah.
And is the converse true?
Actually, converse is easier to prove. Because you just take the infinitesimal element, right? G is equal to 1 plus identity plus. Yeah. To go back to the group, you basically just use exponential map. I mean, from the Lie algebra to the group. Okay. So this is and the representations are very important for both mathematics and physics, right? In physics, the group theories appear through their representations. So typically what will happen, there will be some fields, let's say some fermion fields or bosonic fields and so on, and they will transform under the group, under some group, in a particular way. So that's exactly the statement that you are taking. So that transformation, which is, now you see the fields are written in terms of some column vectors. Fields, in some column vector, some n-dimensional column vector, on which the symmetry is acting. So that symmetry will be represented by an n by n matrix, that symmetry action. So from n by n matrix, and so just one second. This very important thing is to study the representation theory, and that will be one of the main subjects actually later on. Sorry, go ahead.
In that part, G and H are elements of the group or the algebra?
So here when I use capital G, I mean group.
But here L is defined.
Yeah, so typically I will use, just to be consistent, I will try to use the script G and the calligraphic G for the Lie algebra, and just a capital G for the group. So this is group, and this is the Lie algebra. And when I use this capital X, capital Y, etc., they will always be elements of the Lie algebra. And when I want to write the elements of the group G, I will use this little g, little h, and so on.
But then so the function R acts on elements of the algebra and the group.
Yeah, yeah.
So the output is always an n by n matrix, which is
Yeah.
algebra or group.
It will be, no, so this is a one representation. I mean, there are infinite number of representations, right? So, so let's say, suppose I have a map here. I have a map to n by n matrices. And similarly, the group is also mapped to n by n matrices. Okay. But what I'm saying is that, I mean, you can discuss this independently. It's not, representation of Lie algebra is defined through this relation. That you have a map, linear map, which preserves this vector space structure. Okay. And, one more thing, very important thing which I forgot, which is the commutator structure. This was just the vector space structure. The commutator structure is that if I take the commutator of xy, this is the most important thing, I forgot to mention that. So suppose the x and y are in the Lie algebra. Then I know the commutator is also in the Lie algebra, right? So this will also be mapped to some n by n matrix. Because when I say this map is, every element of G is mapped to, every element of the Lie algebra is mapped to n by n matrix. So in particular, this is also an element of the Lie algebra. So this should be also mapped to some element. But the important point is that this map should be such that it is the same as R of x commutated with the R1. Where this is just the matrix commutator. These are all n by n matrices. You take the matrix commutator. So, I mean, in brief, basically what we are saying is that whatever structures you have on the left-hand side, so in the Lie algebra, you have the vector space structure and the Lie bracket structure, right? These are preserved under this map. That is the main point. Huh? So the vector space structure is preserved if this is true, right? And the commutator structure is also preserved if this relation is true. This is there. And here at the group level is just a composition rule. This will automatically, I mean, if you now restrict this to the infinitesimal element, then it will automatically satisfy these conditions.
Can you put that from this condition?
That from this is by exponentiation. So you have to exponentiate. I mean, you have to exponentiate these elements.
So, you can get that from.
You can get from that, yeah.
So, what if we want something else to represent a group, for example, differential operations? Can we do that?
Well, differential operator, what kind of differential operators?
Because differential operators are also, linear differential operators, the linearity and property. They will also.
Okay. Yeah, I mean, sure. You can do that, but those will be like infinite dimensional representation, right? Because those differential operators are going to act on space of functions. Space of functions is always infinite dimensional. So here, for simple, of course, that also plays an important role in physics, right? For example, the angular momentum generators, right, which generate SO3, right? So, but those guys act on the a priori to begin with infinite dimensional function spaces.
So generically, is it easier to find a finite dimensional representation or the infinite dimensional representation of a particular group?
Okay, we'll be always focusing on finite dimensional. But even, let's say, SO3, when you write as differential operators, at the end you're always going to the finite dimensional representations, right? By fixing a particular angular momentum. Then you get 2L plus 1 dimensional representation.
So is it always true that if you find an infinite dimensional representation, then from that representation you can find a finite dimensional representation?
No, not necessarily. There are genuinely infinite dimensional representations which are irreducible.
Okay.
Yeah. I mean, it depends on the various groups, right? I mean, there are groups where, in SO3 case, everything, I mean, you can, if you talk about unity representation, then these are all finite dimensional representations.
So if the infinite dimensional representation is reducible, then you can get a finite dimensional representation.
Yeah.
How
Like the space of functions, you decompose in terms of spherical harmonics, right?
So how the representation should have a generator also?
Representation, I mean, it's a, well, I mean, you can call it as generator. I mean, these are all, because they satisfy the same equation, same conditions. No? So you can call this R of x X and R of Y is the generator. Right.
So there must be a relation between the generator of the group and representation.
Yeah, I mean, actually we'll see the example now. Okay, we'll see. In fact, right now, actually, the way we do proceed with the SU2 is to construct a representation of SU2, and then show that that actually is the SO3 matrices. So that's true. Yeah, that happens, right? Yeah, you can do that. Yeah. Right. But of course, what will happen is that, I mean, here, let's say, I mean, the definition is more complicated, right? I mean, if you want to define, let's take SO3. You already know the SO3 from quantum mechanics courses, right? So SO3 is 3 cross 3 matrices, right? 3 cross 3 matrices, which are orthogonal. Matrices special, so orthogonal. And at the level of this, the group level, at the level of Lie algebra, which I will use a small s to distinguish between small SO3 is a Lie algebra, capital SO3 is a group. This will be the space of 3 cross 3 antisymmetric matrices, right? This we saw, I think, before we saw it, right? I think one of the earlier lectures we defined the generators, right? Just like for SU2, we found that the generators were 2 by 2 Hermitian matrices, right? Traceless Hermitian matrices. In the case of SO3, we have antisymmetric. Or if not, we'll discuss again this later. But at the moment, let me just mention this. Antisymmetric matrices. So that is what it is. But now suppose I go to, this has all sorts of representations, right? Spin I mean orbital momentum 2L plus 1. Orbital momentum L, orbital angular momentum. Then this is 2L plus 1 dimensional space. Right? This you know from the quantum mechanics course, right? Now, so this will be a 2L plus 1 dimensional vector. So this representation will be 2L plus 1 cross 2L plus 1, right? Matrices. The way it will act will be 2L plus 1 times 2L plus 1 matrices. So of course it's true this SO3 will be a subset of the 2L plus 1 dimensional matrices. No? But not the most general, because SO3 is only 3 parameter, it's 3 dimensional. A 2L plus 1 cross 2L plus 1 matrix is a much bigger dimension, right? So not any 2L plus 1 dimensional matrices will appear when you look at the representation of SO3. It will be a 3-dimensional subspace of that. Okay. So that, I mean, that was I think, so you see that matrix, that subspace of the matrix. So the SO3 is mapped to say 2L plus 1 cross 2L plus 1 matrices, right? SO3 Lie algebra is mapped to that.
But it should also be an anti-symmetric matrix.
Anti?
It should be the subspace of the anti-symmetric 2L plus 1 cross 2L.
But that's still too big. I mean, its dimension will go like L square, no?
Yeah.
But this is only 3-dimensional.
I'm not saying that it should be the whole space.
Yeah.
That it should be that space.
Yeah, it will be certainly that, but it should be much smaller than that. Because just 3-dimensional subspace, right? You are mapping 3-dimensional space inside 2L plus 1 times 2L plus 1 matrices to begin with. You can make it antisymmetric, so it will be 1/2 2L plus 1 times 2L, right? Matrices. That is the parameters in there. So this is mapped to some 3-dimensional subspace. So that 3-dimensional subspace will satisfy the same as SO3 algebra. Right, so yeah. Okay, so let's now go to this thing. So there are lots of representations, as you already see here. I mean, for any L integer, so 0, 1, 2, 3, there is a representation. Irreducible representation, actually, in fact. And these are different representations. So in general, there is always an issue how we can construct all the representations of a given Lie algebra, no? Or corresponding with Lie group. But let's focus on the Lie algebra. Okay, this is a difficult question, but it turns out there is one representation which comes for free. That is the adjoint. Of course, the trivial representation is free. I mean, the trivial representation is where every element of the Lie algebra is mapped to 0. Okay. 0 clearly satisfies this condition because is suppose everything is mapped to 0, x, y, everything is mapped to 0, then of course Rx is 0, Ry is 0, any number, this is also 0, and the commutator of 0 with 0 is 0 also. So 0 is a trivial representation. That is what is called the one-dimensional representation, right? So every Lie algebra is a one-dimensional representation. The rest too trivial. So a non-trivial representation comes for free. That is the point, and that is the adjoint representation. Adjoint representation comes for free because.
What do you mean that
For
comes for
free.
free?
Comes for free meaning that you don't. The knowledge of Lie algebra itself is sufficient to construct the representation. You don't need any more information.
Natural. Natural.
Natural one, yeah.
Oh, okay.
Exactly. And what is more important is that this representation, a study of that, a joint representation, really teaches you a lot. I mean, we'll see that in this entire course, that from the joint representation, you can understand the structure of the Lie algebra completely. So it's very rich. I mean, you can really completely understand the structure of the Lie algebra by studying a joint representation. So we will see that. Huh?
And the commutator become very simple.
Exactly. This is the commutator. Because precisely. Yeah. So it has all this because the whole structure of the Lie algebra is in the commutator, right? And that commutator is captured in the adjoint representation. Okay, so we'll look at the adjoint representation of SU2. So what is the adjoint representation? So the representation just starts from, so imagine again, let's draw this picture here. So here is my identity. Okay, this is a 3-sphere. So now consider two elements, G and H. Then of course I can define G, H, G inverse HG, right? This is certainly again an element of SU2 or any group, for this matter any group, right? Now imagine, so take H to be a function of a parameter, let's say psi. Okay.
A single parameter.
One parameter, let's take one parameter. So when you take one parameter family of this H, a continuous one parameter family of the H, then it's going to define a line, some curve, one-dimensional curve, right? Because at every value of psi, if you start plotting, so I will impose the condition that H of 0 is identity. So this is going to be some curve, which will be like, say I just draw it like this. Huh? So H of 0 is here, H of say 0.1 is here, and so on and so forth. Huh? So it's going to be a continuous curve, because psi is a continuous variable. So define a curve. So now I consider this. Okay. So whatever it is, whatever the result is going to be also depending on, G is fixed. I fix the G. I just fix the G and then consider this. Now at psi equal to 0, so this is going to be something. I don't know, what shall I call it? K, let's call it K. So K is G inverse HG, which of course is also going to be a function of psi. Right? Now this will have the property that at psi, so K of 0, at psi equal to 0, well, H of 0 is identity, so G inverse times G is also is identity, so this is identity. Okay. So you see what we have done here is that, so this curve, so here is my H of psi. Okay. K of psi again starts from psi equal to 0 is identity, or maybe it is some more complicated curve. And the precise curve will depend on what G you are choosing. G is something you have chosen, let's say. If G was identity, of course this will be the same curve. But if G is different from identity, in general it will be some different curve. Right? If the group is abelian, it will be the same curve. Right? But if group is not abelian, in general it will be a different curve. So, but now the point is that this. Now let's look at the infinitesimal version of it. Just take derivative with respect to psi on both sides. Okay, first derivative, and then set psi equal to 0. Okay? That gives you the Lie algebra element. So this tells you that there is a map from the Lie algebra element to another Lie algebra element. Right? So idea is that you take the derivative d by d psi of both sides. So this is going to be G inverse. This does not depend on the parameter xi. It only h depends on xi, right? So this is going to be dh over d psi G. This is the Lie algebra element, and then set xi equal to 0. When I do that, I get a Lie algebra element here. And this is also going to be the algebra element because K had exactly the same property. It's elements of the group with a condition that K of 0 is identity. So when I make a Taylor expansion around that, I'm going to get again the algebra element. So this tells you that there is a natural map from the Lie algebra to itself, right? So you think of this as a map. So this, I don't know, let's call it some map F, which of course depends on the G. This takes H psi. So this is a symbol. This by definition is that. So this is just to illustrate that there is a map which depends on the G, right? Which takes a group element X psi to K psi. Okay. But now I look at the infinitesimal version. Then it says that this map takes a Lie algebra to itself, because both have the Lie algebra of the same group, right? Both elements here, this and that you get. So it's a Lie algebra to itself. So there is a map. That's a linear map. You see, it's I mean, if I take h psi, I mean, take the derivative of this plus another term, is obviously linear map, right? The Lie algebra structure is preserved. Vector space structure is preserved, and Lie algebra also you can show by just start taking the commutators. Okay, you can show that this is a linear map, okay. And which preserves the commutation relation. So the upshot is that we have found a map from the Lie algebra to itself, and this map is not just one map; it depends on G. Right? For every element G. For every group element G, I can associate a map. And the map is simply given by this, G inverse. So the map is just given by G inverse times, okay, if I write like this, 1 plus a Lie algebra element, X, G. So 1 doesn't do anything, identity doesn't do anything. So what is left over is simply identity plus G inverse XG. X is a Lie algebra element. This is important, so that this operation is giving you back again in the Lie algebra element. Okay. So, for example, let's just check that, I mean, just to be sure that this is correct. I mean, this makes sense. Take SU2. SU2, by definition, the Lie algebra elements were polymatrices, generated by polymatrices, sigma 1, sigma 2, sigma 3. Right? Any element of the Lie algebra can be written as linear combinations of these three. Right? Now, the question you can ask is it true that if I take the SU2 group matrix, G inverse, and multiply by sigma, say, A, and again multiply by this. So these are all 2 by 2 matrices, 2 by 2 matrix multiplication, where G is one of those guys which we wrote, no? Which we wrote Z1, Z2, what was that? Z1 bar minus Z2 bar, right? Something like that, yeah. And the inverse of this. So inverse of that will be what? Okay, I just write this inverse, Z1. We will not need the details of that. So if you multiply that, the exercise to show that this is the same as, again, a linear combination of sigmas. You can try that, try to check that this is true.
Can you show it for an arbitrary group?
Arbitrary group element, yeah. Arbitrary group, yeah, you can, well, I mean, for matrix groups, you can explicitly work it out.
Yeah.
But in general, I mean, this argument already shows that. You see, this was just a double check. No? This argument already shows that this is a map from Lie algebra to itself. No? Because the infinitesimal element here will be mapped to the infinitesimal element there, right? By continuity from this relation. So this is, but you can check it explicitly. In fact, it's easier to check in the following way. Let's suppose G itself also is a infinitesimal element. Okay. Then what will be this? Suppose G itself is infinitesimal. So say identity plus say some y, where y is some infinitesimal. To order the first order, then higher order terms will be there. But look at the first order term, right? G. So I mean, imagine there's some parameter here, epsilon. So epsilon is small. Then there will be epsilon square order and so on. Okay. So take an infinitesimal element. Okay. Then what does it be? What will it be? This. So G inverse is clearly identity minus epsilon y plus order epsilon square. Right? And then this relation, so G inverse xg simply becomes, okay, identity takes it to x itself. Right? Now look at the difference. What is the change in that? That change will come from, it will be basically commutator of, or maybe minus the commutator of yx. Minus because of the way I have defined it. Yeah? It's a commutator of yx. You can just plug that in. G inverse here and G there, and collect the order epsilon term. Okay. You get this. So the change in x is given by yx to first order, the commutator yx. So the adjoint representation is simply given by the commutation relation itself. That's why you don't need any other structure. Just the commutator itself defines to you a representation.
So here y is the generator of the element G.
Y is parameterized in the element G, infinitesimal element G.
The generator.
Yeah, I mean G is an arbitrary element, but I'm saying that this is true for any arbitrary element. Now it doesn't have to be an infinitesimal. G need not be infinitesimal. But let us focus on now when the G is also infinitesimal. Infinitesimally close to identity. Okay? Since this is true for every G, this map exists for every G, it will also exist for an infinitesimal element. Right? Then if you study what happens near the infinitesimal element, this just gives you the commutator. Right? So the commutator itself gives you the adjoint representation. That's what I'm saying.
So what if I chose the member of the group G, which comes actually from the same generator I'm using?
Okay, it will be 0.
So, yeah, so I get another generator which is the same as the one I already.
No, I mean if y happened to be x itself, then the commutator is 0. It just tells you that.
So I can't use the member of the group that comes from the generator I use.
Yeah, you can. This is a general statement. Okay, if that happens, if G was coming from the same, I mean, where it was here. If G was coming from, I mean, x, exponentiation of x, then this is simply x. Nothing happens to it. X remains x. No? It changes. But that's a very special case. No? I mean, this is a statement for every. So just like here, we said this is f of G acting on psi. At the level of Lie algebra, once I think of G itself as a infinitesimal element. So remember, so what did we do? So this thing is, maybe I should write it more clearly. Maybe I should write more clearly here. So when we do this, then we said, so this was a map. I mean, this was a general map. Fg acting on x was nothing else but G inverse xg. Okay. Now I want to ask what happens to f of when G itself is an infinitesimal element, 1 plus some epsilon y. Then f of 1 plus epsilon, 1 is identity, plus epsilon y, acting on x is going to be, from this relation, we find that this is the x itself plus to the order epsilon, what I find is the maybe x commutated or minus y commutated with x. So, I can define a new function f of y, because here the identity is fixed, right? All you're changing is y. Y is what you are changing, considering different y's. And for each y, we have a map for each y. Okay? So f of y acting on x is simply the commutator yx. I define this. Of course, now we should check. I mean, okay, this was of course motivated. Of course, from this kind of argument, it's clear that this is a representation. But just to double check, let's just double check it. Since okay, let's just double check that. Does it satisfy all the conditions that we have? This is a linear map. So in particular, first of all, I mean, this doesn't look like a matrix, right? We said representation is a map from the Lie algebra to some n by n matrices. But you can easily convert it into matrices, understand it as a matrices, because let's choose some basis TA for the Lie algebra. Then I can expand x as some coefficients, xa, ta. Right? And then xa, I can think of it as some kind of column vector, x1, x2, up to xn, up to xd. Say d is the dimension of the Lie algebra. Okay, so I can put them together in terms of some column vector. Now, what is going to happen if I commute y with x? Okay, it's going to be xa and y commuted with ta. Right? Now, y commuted with ta is again some Lie algebra element, right? Therefore, I should be able to expand again this thing in terms of the Lie algebra generators, right? In terms of this basis. This is the basis, right? This ta are the basis. A going from 1 up to b is a basis, which means that any element of the Lie algebra can be written as a linear combination of the TA. Now, this is an element of the Lie algebra. Therefore, I should be able to write it as some linear combination of the TAs themselves, right? So, so it's going to be, so I put here XA, and then this will be some combination, say Y, let's call it YAB TB. Right? So you see this YAB, these are the coefficients. This depends on the Y, right? Which Y you choose. So this YAB is you see it as a D by D matrix, because A goes from 1 to D, B goes from 1 to D. This is a D by D matrix. So that is what I mean by map. Yeah? So every Y, so now I can write this transformation as this matrix Y, Y11, Y12, etc. Okay. Maybe the way I've written is probably the transpose, maybe is Y11, Y21, but that doesn't matter. So you have got this D by D matrix, and what we are doing is, so I started with some XA. Now what has happened? This guy is some X prime B, right? So XATA has gone to some X prime B TB. Okay? So the change that has happened due to this action is XA has gone to X prime B. XA goes to X prime, X goes to X prime. Okay? And this formula relates. So this is X prime 1, X prime 2, etc. X prime, these are simply given by the matrix, this Y matrix times X1, X2. So this is what I mean by the map. So Y is mapped to this matrix. And this is for arbitrary Y. Right? So every Y is mapped to some B by D matrices. Now, so let's now see the properties. I mean, all the properties are satisfied or not? Is it a representation? Because we have the condition of linearity, right? And so the linearity, you can see that is obvious because the commutator is linear, right? I mean, our thing was, so if I look at, what shall I call? Ry I can call, right? Ry, I was calling here Fy, but I just call R because R is what we use for representation, right? So since we now see that this is some D by D matrices, right? I just call it as Ry. Ry are acting on X, say, I don't know, alpha X plus beta X1 plus beta X2. This clearly is linear, right? Because the commutators are linear, right? If after all, what was it? This was nothing else but y of alpha X1 plus beta X2. But this is the same as alpha yx1 plus alpha yx1 plus beta yx2, right? But that's the same as r of x, alpha times r of x1, ry of x1. I don't know. Is it confusing, this symbol? Sure, because there are two brackets here. Yeah? Maybe this I should put as a subscript here. Yeah? I mean, Ry is a particular matrix corresponding to y. Now that's acting on this. Okay, so maybe that's better. Otherwise, there are two brackets here, so it's confusing. Ry acting on x1 plus beta Ry acting on x1. That was the linearity we mentioned, right? And similarly, also you can do the following thing. I mean, there's a linear structure here, but there's also a linear structure there, because I can choose R of, let's say, alpha y1 plus beta y2 acting on x. Right? This is the same as the commutator alpha y1 plus beta y2 acting on x, the commutator of that, which is the same as alpha commutator y1 x plus beta y2x, which is the same as alpha r y1 acting on x plus beta r y2 acting on x. So the linear structure there also, right? I mean, I can add two different y's with some coefficients. The matrix that this is mapped to is the same as the alpha times the matrix that y1 is mapped to, and beta times the matrix y2 is mapped to. So the map is linear. The map from the Lie algebra elements to the D by D matrices. This is a linear map. But now the most other important thing is to check the Lie algebra bracket. The commutator, is it preserved or not under this map, right? So what we want to check is if you have, let's say, two elements, y and z, and I have this map which maps this element ry to a D by D matrix, and this element to rz to another D by D matrix, right? But I have also the commutator yz, which is mapped obviously to some r of this element, which is again another Lie algebra element, yz. Now the question is it true, what we want to check, is it true that ry z is the same as ry commuted with rz? This is what we want to check. So how do you check this? Well, basically these guys are defined by their action on an arbitrary vector x, right? So we want to check the following thing: whether this acting on an arbitrary x, is it the same as this acting on this x, on the same x? That's the question, right? If you can show that this is true for every x, then we have proven it, right? Exactly, that's a point, Jacobian. So let's see, then we can just do that. So this object, this is simply the commutator of yz with x, right? It's just the commutator of whatever this is with that, right? So we want to check whether this is the same as, here is the commutator. So there are two terms here, right? I open it up. So it's ry and then acting on rz x minus rz acting on ryx, right? Sorry, yeah, correct. Right? This notation is correct, right? What does this commutator mean? First rz acts on x, then ry acts on that. I mean, first rz acts on it, you get something, this, right? Then ry acts on that, because this guy is again a Lie algebra element, right? So, again, and the other way, opposite order. Commutator has two terms, right? Well, this guy is nothing else. This is nothing else but zx, that one. And now when y acts on it, it is a commutator with the y. And here, this is yx. And then rz acts on this, so it is z. And you can verify that this is exactly the Jacobian identity. You just put them all together. Okay, you have to flip the sign, so put this, I mean, maybe exchange these two. Okay. And you can see that this is nothing else but Jacobian identity. So you see, Jacobian identity was quite crucial. So far, Jacobian identity never played any role, right? Well, because we were always thinking in terms of matrix algebras and so on, matrix groups. So Jacobian identity was automatic. But here in a more abstract setting, because now we are thinking in a more abstract way, here in this blackboard, the fact that this gives you a representation, I mean this definition, there was a definition, yeah, this ry of x is simply, this was what was, I forgot, ry of x, we said it's nothing else but the commutator by x. So this gives a map from x, from the Lie algebra itself, right? That this map is in fact a representation. I mean, so there are several steps. This was a map, but this map now I can always think in terms of as a d by d matrices. So really this map is a d map from the Lie algebra to the d by d matrices, right? Because for each y, I can think of it as a matrix, d by d matrix. So this ry gives you a map from y to a d by d matrix. Then we saw that this map is linear, it satisfies all the linearity properties. Okay. And finally, we need to check whether the commutator structure is also preserved. Okay. And that is automatically guaranteed if your Lie algebra satisfied the Jacobian identity. It's completely automatic. Okay. So we see that there is always, given a Lie algebra of dimension d, there is a d by d matrix representation, right? And that, so it's completely tied with it. You don't need to do anything more. It's already just from the Lie algebra, and that is what is called adjoint representation. It's a terminology. I don't know the historical reason why it's called adjoint, but okay, it's adjoint. It's called adjoint representation. So this representation is adjoint. Okay, so this is fine, but now let's go back to the SU2. Now, this is general discussion, right? Now we specialize to SU2 case. Okay.
How did you define the fundamental representation?
Yeah, fundamental representation, of course, already this two-dimensional sigma polymatrices were 2 by 2 matrices. Yeah. So that was already a representation.
In general?
So in general, okay, for the, as I said, in this course we'll be only discussing matrix groups. So the groups themselves are defined in terms of some matrices. So that defining, the definition itself uses some matrix, say n by some k by k matrix. So that is the fundamental representation.
Okay. And the fundamental?
Anti-fundamental, we'll study that. We'll see that when we come to SU3. In SU2 there's no difference. Fundamental, anti-fundamental is the same. The difference starts at SU3 and higher.
Okay.
Yeah, we will study that in detail. But maybe not next week, the week after, we'll start studying SU3. Because I still have to do a joint representation, and then we'll discuss this week, and in this week we'll discuss all the representations of SU2, which you already know, but I will try to do it to maybe, I think different people here may have seen it differently, the representation. Some people may have seen in terms of differential operators, the way it appears, the Schrodinger equations and so on. No? Some people may have seen it in a more algebraic approach. We'll be using the algebraic approach, the algebra approach. So, okay. But you already know the result, but it's just a way of seeing it. So I will just go through it because it is crucial. It's crucial that you understand SU2 representation. Because if you don't understand SU2 representation, there's no way you can understand SU3 and higher Lie algebras. So it's crucial that that is completely clear. SU2 is completely clear. So even though I think you already know, but I will go through it very slowly this week.
Can we normalize this matrix according to our desire? Such that the trace becomes something,
Polymatrices.
No, I'm talking about general groups. So, this metric that we, is associated to the, that commutator of y and x. Can we normalize it so that if we multiply two matrices, they become traceless if the matrices are not same?
So let's say two different matrices of the same d n by n, d by d matrices, you multiply and then?
And if you take the trace, it becomes 0 if the matrices are not same, because when I was learning about it, it said that we can normalize this matrix according to our desire. It is conventional to do that.
Oh, the basis, yeah, basis you can choose anything.
You can choose any basis.
Yeah.
From basis, so is it mandatory that such a basis will always exist in which the trace becomes 0 if the matrices are equal?
No, that is not necessarily true. No, it's not true in general. No.
Not true in general.
No. I mean, already for SU3 you see it's not true, right? Because you take, you're talking about Lie algebra, right? Not the group. The Lie algebra, if you take SU3 is a 3 by 3 traceless Hermitian matrices, right? So in general there will be two diagonal matrices. Even take a simple case. There will be two independent diagonal matrices. You take the product, so they're different. I mean, take example. If we take this matrix, 3 by 3. So SU3 will be a 3 by 3 traceless Hermitian matrices. Right? So take an example. So 1 minus 1 0. Okay? Another matrix 1 0 minus 1, for example. If I take these are different matrices, right? Take the product, trace is not 0. Okay, the product is 1 0 0. No?
So maybe if you change the base, can we achieve that?
No, not really. No. Yeah, okay, you can change the basis. Yeah, sure. You can choose, in this particular case, you can choose 1 minus 2 or something, right? Then it will become traceless.
That is gamma 8 matrix.
Gamma 8 matrices, yeah. Yeah, okay, you're talking about the killing form. Okay, you're talking about the Cartan killing form. Yeah, Cartan killing form you can always diagonalize. Cartan killing form, right? It's a metric on the Lie algebra space. So if it's non-degenerate, you can always, you can diagonalize it.
So, we can set it matrix, the matrix, which is, more similar to the metric of a flat space.
Yeah, you can do that, yeah. You can do that. At least it is true for, I think, all the Lie algebras we'll be studying. In some cases, Lie algebras do not even have positive definite metric. You can have these non-compact algebra groups. We are only going to talk about compact groups.
Can we make it proportional to the identity matrix? Have all this, the Cartan.
Yeah, that is sure, yeah, you can do that. Because the metric is always going to be symmetric. So, there is always, you can choose a Wehrbein, what is called technically, I never heard about Wehrbein, but there are some, you can write the metric as the square of another metric, another matrix. The metric is a matrix, right, as some in d dimensions d by d matrix, symmetric matrix. You can write it as a square of another d by d matrices. And then you can you just redefine your variables, no? By multiplying with the square line. No? Change the basis. Then you can, yeah, that you can do, this diagonalization of that. But that is, I mean, if it is, diagonalize you can always do. Even if it is a negative signature, you can always do that.
Even diagonalize it, it is not necessary that you will make it proportional to identity map. So it is more stronger condition.
No, if you diagonalize, you can just change the, I mean, once you have changed the, so in some basis you have, say, suppose you have diagonalized. Eigenvalues x1, x2, x3, just square root of x1.
Yeah. Scale the, okay.
Yeah, yes, you can scale it. This is scaling. So, okay, so let's focus on the SU2 case. So we have 3 generators. Say T, which let me see. Let me use the same normalization that we use here. Whether sometimes I must warn you that in this note sometimes we use Hermitian generators, sometimes we use anti-Hermitian generators. So anti-Hermitian means just multiply the Pauli matrix by I. No? So there has been, it's a bit.
Probably if you are mathematician, you will use anti-Hermitian.
Mathematicians prefer the anti-Hermitian. Strange, right? Okay. Yeah. Yeah, so we will here just use the Hermitian generators, Pauli matrices. Okay. So we have this map. So this instead of R is for general representation, right? But because this representation is what we call a joint, right? So we'll change the name and we will call it AD. AD is short form for a joint. Right? Okay. So this is a particular representation, which is universal. Every Lie algebra has a representation. So AD, I didn't bring the. So AD, say G, acting on. So we said on the Lie algebra X, right? But it is clear that it is sufficient to specify the action on a basis, right? Because anyway, the whole thing is linear. So if you specify the action on the basis of the generators, then you know the action on everything, right? So I might as well choose the basis for SU2 are the sigma Pauli matrices. Sigma A, so A goes from 1, 2, 3. Right? So at G acting on say sigma A is what we said, G inverse sigma AG. Right?
Is it necessary that the joint representation is irreducible?
No, not necessary. Not necessary. I mean, that will happen. I mean, we'll see later on. There is a classification of the Lie algebras. There is something called simple Lie algebras, and there are semi-simple Lie algebras. Simple Lie algebras is irreducible. Is irreducible.
That joint representation is irreducible.
Yeah. Yeah, I mean, it's not generally true.
So is it true for SU2 and SU3?
SU2 and SU3 are simple algebras, yeah.
Okay.
Yeah. U2, for example, is not.
But we don't need in physics.
Well, yeah, but you have SU2 cross U1, so it's almost like U2, right? U1, by the way, what do you think about the U1 algebra, U1 Lie algebra? And what is the adjoint representation of U1? From this definition, I mean from the way we have defined. So suppose I started with the U1, which is even easier than SU2, right?
It doesn't. It's trivial.
It's trivial.
Because there's
Because there's commutes, right? U1. Because this thing, I mean, at the level of, this is at the level of group, right? But at the level of algebra, it was simply the commutator. But the commutator is all 0. That means every Lie algebra element, for a abelian group, the algebra will be what? Algebra will commute completely, right? So all the commutators are 0. That means a joint representation is trivial. It just, every element goes to 0. Right?
Because we have one unit.
You have what?
One generator for the group.
For the U1, yes, but I mean, take some abelian Lie algebra. I mean, I could take U1 cross U1, I mean, U1 to the power of n, no? For example. So you have n abelian Lie algebras, right? N abelian things. But they all commute with each other. So all the commutators are 0. So therefore, that's a trivial representation in the joint case.
And if we want to have the trivial representation in an arbitrary group, then we can choose G to be identity.
Yeah.
Or G to be,
Yeah, every element goes to identity. I have a unit matrix. Yeah. That is obviously preserved. Any group multiplication will be preserved, right? Because after all, if G is going to identity, H is going to identity. G times H is also going to be identity. So that's always there.
We can generally say that if G is chosen to generate the representation of a particular group, then G will go to identity. No. Probably G will go to identity.
Repeat that again. If G is what?
If G is taken as the element which will generate a representation, then I think G will go to itself, not identity, because G inverse G is.
Correct. Yeah, and add of G, acting on G will be G itself. So sorry, you want to the end. So let's see. I mean, we have already seen from general argument that this is going to be element of the Lie algebra, but now let us just explicitly check it. I mean, that we had a more abstract argument there, right? But here we can explicitly check it. After all, what were these polymatrices? These were the basis for all the 2 by 2 Hermitian traceless matrices, right? That was the basis. So all we need to check is whether this is Hermitian and traceless, right? Well, traceless is clear because trace of G inverse sigma AG, well, you can cyclic property of the trace. So that is the same as trace of sigma A, which is 0. So this is whatever it is traceless. And second, the Hermitian condition. So we want to check if G inverse sigma AG dagger is the same as G inverse sigma AG. Right? This is what we want to check. So we can check that dagger will make it G dagger. Sigma A is Hermitian, so the sigma A remains sigma A. And we have G inverse dagger on the left hand side. But G is an element of the SU2. So it's a unitary. So G dagger is G inverse. Right? So this guy is G inverse. Here is sigma A. And G inverse is G dagger. Dagger is G. So that's that. So you see it's a Hermitian. So this implies Hermitian. So therefore, it is guaranteed that whatever this is, I should be able to expand it in a basis of polymatrices. Right? I should be able to expand. So this guy is going to be some combination. And let me use the same notation here. Yeah, NAB. So it will be some linear combination of sigma B. Right? So you see, so this notation, and of course it will depend on G, because which particular linear combination will occur will depend on G. Right? For example, if G was identity, nothing happened. This will be just a Kronecker delta. Right? Sigma A will go to sigma A. It will be identity matrix, right? But in general, this is going to be some linear combination, but the coefficients will depend on G, which G you are talking about. And this notation is the following. You see, there are two indices. A, because I'm expanding this guy, which has the index A, right? This is going to be some linear combination of all the polymatrices. So it is going to be a linear combination. This is defined by sum over B, sigma B. But the coefficients will depend on which A you started with, right? So I'm just, this notation is just keeping track of that. What did you start with? Left hand side. Left hand side you started with sigma A and G, and that information is there. But written this way, you see that this NAB is a 3 by 3 matrix, because A can go from 1 to 3, because as I change 1, 2, 3, I have this A goes from 1 to 3, right? And B, of course, is manifestly. This is repeated indices means sum. Yeah? So this B goes from 1 to 3. So MAB is M is a 3 by 3 matrix. And the matrix itself depends on G. Okay. Now the important point here is the matrix M is real. MAB are real. Right? That is clear because this has got to be Hermitian. Right? If any sigma is multiplied by I, it is not Hermitian, it will become anti-Hermitian, right? So every sigma has to be multiplied by real numbers. So that's MABs are all real. And I mean that has to be true for every G and every A. Right? So these are all real. Okay. Now, the important point that what we want to prove is that MAB actually belongs to SO3. That's what we want to check. So the way the proof goes, so in order to do this, I need to check that this is orthogonal matrix. So this is a real matrix, and this is orthogonal, and determinant is equal to 1. Right? These are two things we need to check. So for this, what we do is if you want to prove orthogonality relation, of course you need to take the product of two M's, right? Two matrices. So let us start from the G inverse sigma AG times G inverse sigma BG. Let's consider this. Okay. So this will involve, when I expand it in the sigmas, this will involve 1M, and this will also involve 1M. So you have some product of two M's roughly, right? Which you need in order to prove that it is orthogonal, right? Orthogonality relation was that M transpose M is identity, right? That was the orthogonality relation. So we need to prove that. So that's our aim, but let's start looking at this. Now this is nothing else but this G inverse cancels, so you get here G inverse sigma A, sigma B, G. This one itself, sigma A times sigma B is delta AB times identity matrix plus I epsilon ABC sigma C. Correct. That's a polymetric satisfies this condition. So now you see I'm using the very explicit form of the polymetrics.
Just 2. Factor of 2.
Right.
No, it's not the commutator. I'm not taking the commutator. You see, otherwise delta AB will not be there. Just a product. So suppose I take sigma 1, sigma 1. Then of course this will be absent because this is antisymmetric, right? And you just get 1 identity. But if it is 1, 2, sigma 1, sigma 2 will be I sigma 3. But when you take the commutator, then you have a sigma 1, sigma 2 minus sigma 2, sigma 1. So each one gives you a factor of 1, that makes it 2. Okay. So it's not a commutator, yeah, important thing. It's not a commutator. I'm not taking commutator here. So it's using a bit more information than the algebra, you see. It's a very specific nature of the polymatrix is being used here. Because if you are going to use only algebra, then you should be only thinking of commutator.
And anti-commutator.
Huh?
And the anti-commutator for describing the whole.
Yeah, but I mean anti-commutator, that's a very peculiar thing about the polymatrices. That you can talk about anti-commutator and so on and so forth. In general, there is no such thing, right? In general, the only structure that you are given with is the Lie algebra structure, commutator structure. No? But here we are using more. And that is here, this relation. Therefore, this is simply delta AB times G inverse G will be delta AB times identity. Plus I epsilon ABC G inverse sigma CG. But this by definition was, okay, there's I epsilon ABC, and then here you have M C, this index is C now, right? And that index, I don't want to use the same B, it's a dummy index, right? Sigma B, correct? I mean, this is, with the indices, when you play around, you should always be careful with the index, no? I mean, you shouldn't repeat that index somehow. And that mistake is common. I mean, I make that mistake many times in doing the calculations, And then at the end you see, what the hell is going on here, You get nonsensical results, So you should be careful about that. Okay, so that's that side. But on the other hand, I could have used this relation already here. Each of them, so this one is MA, now I shouldn't use B here, something else, let's say E, G, sigma E, and MB. So these are numbers, and so the matrix is just this. I mean, the 2 by 2 matrix is here. MB, let's say F, sigma F. So what I did was, here I just directly use these relations. So I'll get a quadratic term in M. Right? But here I use the polymatrix algebra to write it in this way. So this will be delta AB times identity plus something times a single M. Okay. Now this again I could simplify. So left hand side. So right hand side I don't touch as it is. Left hand side I can write it as M A E M B F, and then we have a sigma E sigma F. Right? The sigma E sigma F, again I use the polymatrix algebra. So that is delta E F times identity plus I epsilon E F K, let's say, sigma K. Okay. So this is this equation, I mean this is the left hand side and this is the right hand side. Okay. So now you see, if you look at this both sides, as far as 2 by 2 matrices are concerned, there's an identity matrix and there are these polymatrices. Here also you have identity matrix and the polymatrices. Now if you look at all the 2 by, I mean these are linearly independent 2 by 2 matrices. So if this equation has to be true, the coefficient of the identity matrix must be the same on both sides and the coefficient of the polymatrices must be the same on both sides. That's the only way this equality will be valid, will hold. So looking at the coefficient of identity, coefficient of the identity matrix, what you find is that M, so delta EF, so you get here MAE, MBE, because delta EF, so F becomes E, right? That is equal to delta AB. That's the relation, right? I mean that this is equal to that. But that's nothing else, is simply M transpose. If you take the transpose, I can write, so let me do step by step. So I leave this as M, AE, and here I write it as M transpose EB, right? Because when you take the transpose, you exchange row and column. But now it's an ordinary matrix multiplication, right? The row and the column. This is the way you multiply the matrices. So therefore, this is nothing else but M transpose AB. And the statement is saying that delta AB, so this implies that M transpose is identity matrix. Identity, but not 3 by 3 identity. Here the identities were 2 by 2 matrices, but now it's a 3 by 3 matrix. M is a 3 by 3 matrix, so this is a 3 by 3 matrix. Yeah? Okay. So this immediately proves that M is an orthogonal matrix. But now we need to also look at the, so this is only one part of the equation, right? Now I have to check also I have to also equate this, the polymatrix part, right? So so let me write down that equation. So on the left hand side I have I epsilon. So I'm looking at the coefficient of sigma k, right? This is the coefficient of sigma k. So I epsilon, what is that? No, MAB, sorry, I should write. Yeah, okay, I epsilon, what is it? EFK, MAE, MBF. That's the left hand side. So this is the coefficient of sigma k. Right hand side, here is D, I've written D, so let me put here K. So that this is a dummy index anyway, so I change it. Okay. So you find here this is equal to I epsilon ABC MCK times MCK, that's it. So these are the coefficients. So this equating the coefficient of sigma k on both sides, you find this relation. Okay. Well, I cancel both sides. Now let's do the following. You have EF. Let me multiply both sides of the equation by, say, let's say dk. Multiply this equation both sides by m dk, and sum over k.
And that's how become determinant.
Exactly. Yeah. So this one becomes this times m dk, and you see you have epsilon EFK, MAE, MBF, MDK. There's nothing else but the determinant of m times epsilon ABD. Right? So this side, I mean, I multiply both sides, right? So this side has simply become epsilon AB, the free indices, ABD times the determinant of m. Right? This you have seen, all of you have seen this formula, right? The determinant formula. So this left hand side is that. What about the right hand side? Well, right hand side is MCK and DK, but that using this equation. So you see, if I put here K, this E is K, this is C, and that is D, right? That is simply delta CD. So when you multiply this here, this and dk, this product and summing over k becomes delta CD. But then that just makes it ABD, epsilon ABD. So here it becomes epsilon ABD. Okay. So the equation tells you determinant of, this equation tells you determinant of n is 1. That's exactly the SO3 condition, right? So we see that this matrix N is exactly the SO3 matrices. Not of O3. O3 would be when you have just this condition, not the determinant condition, right? But what we are seeing is when we go through this, we are getting SO3. Determinant is always 1. But this map is not one-to-one. Let's ask the question. Is it true that this map, so every G gives a 3 by 3 matrix, M, right? This M was a function of G. That action, what we said, G in here. These are all, sorry, I forgot to write, but these are all, there is a G inside here. This I missed. Because everything came from the G inverse sigma G was equal to MABG sigma B, right? That was the equation we had, right? So there is a G, this M depends on the G. So I should put, wherever you see M, there is a G inside here, which I forgot to write in the later equations. So this is G, this is G here, and this is G. Everything depends on the G. That's clear, right? So what is the conclusion? Every G of the SU2 is mapped to an orthogonal matrix, with determinant equal to +1, right? But now you can ask the question: is this map a 1-to-1 or many to 1? No. That's the question. Or is even on 2? Does it cover all the orthogonal matrices, the determinant equal to 1? And answer is that it is on 2, meaning that it covers the full SO3 group, okay? But it is not 1 to 1. It's 2 to 1, and that's easy to see because this is, after all, left hand side is quadratic in G, right? Whereas here you just get M, right? So, for example, if I just replace G by minus G, nothing happens. I mean, minus minus cancels, we get it. So, and minus, if G is an SU2 element, minus G is also an SU2 element, right?
What is the minus
G is a 2 by 2 matrix. G is a 2 by 2 matrix. Minus means minus 1 times that. So this is not abstract. This is a very, we are talking about matrix groups now, right? So it's a, yeah, in general there is no meaning of minus G, right? So the statement is that if G belongs to SU2, then minus G is also belongs to SU2. This implies. So we can check that because the main defining condition is G dagger G equal to identity, right? And determinant of G equal to 1. That's the definition of SU2, right? So clearly this condition G dagger G doesn't change if I replace G by minus G, because G dagger also picks up a minus sign. So this remains invariant. And did G also doesn't change anything because G is a 2 by 2 determinant, right?
Here we are, talking about a representation of SU2, not the SU2 itself. Because, if you talk about the group SU2, there is a meaning of minus G.
Yeah, but I mean, here we are almost, even the polymatrix has no meaning, right?
We are talking about the representation of
It's a 2 by, the way we define SU2. SU2 is defined as 2 by 2 unitary matrices with the determinant 1.
So you're talking about matrix groups.
Yeah. SU2, yeah. SUN are generally defined like that. N by N unitary matrices which are determinant 1. Right? Yeah. So you see that minus G is also an element of SU2. And both of them are mapped to the same. So G and minus G both are mapped to the same N. Right? Because from this map you can see, if I replace my minus, these two minus signs cancel and you get the same N. So it's a 2 to 1 map actually. It's not a 1 to 1 map.
And so then we have to prove that NAB of G is the same as NAB of minus
G.
So then we prove that also?
Yeah, that we prove because, so I mean if I now replace this by minus G inverse, sigma A minus G, well that by definition is MAB of minus G,
Yes.
right? But this minus minus cancels,
Yes.
so this is the same as MAB G sigma B.
No, it's in, yes.
So therefore this is equal to that.
So, in the mathematical context, can we say that the cardinality of SU2 is larger than SU2?
What does mean cardinality? What is cardinality?
The number of elements in that.
Yeah, number of element is roughly twice, but okay, this is infinite.
Yeah.
Both of them are infinite, but twice. I mean, this is a 2 to 1 map. 2 points are mapped to the same point. Yeah, it's right. I mean, in general, okay, this, okay, now I shouldn't make it. I mean, I have to complete this, but let me just, since you asked this question, let me just make one statement here. In SU2, you see, there is a notion, in general, in a group, there is a concept of center of the group. Center of the group. Okay, so this is the set of elements. The set of, so subset, so let's call it, I don't know what, let's call it C, center. So the C is of course, C is a subset of S, a subset of the original group G, so let's say group G. But and G of course in general will not be abelian, right? Okay, abelian is a very trivial case. I mean, in fact, we'll never talk about abelian groups in this course. In general, non-abelian group. But so in general, if I take an element G and G1 and G2, they are not in general the same as G2 times G1. In general, right? In general. I mean, sometimes it can be, but in general, it's not going to be. Right? But center is a set of elements of G which commutes with everything. Everything of the group. So if C is an element of G, of capital C, this I shouldn't use that because, okay. Because when we use this kind of symbol, it means complex numbers. So I shouldn't use that. Okay. So this is some small c. Small c is an element and capital C is a set. So if small c is an element of this center, then of course it's also an element of G, right? So C times G equal to G times C for all G belonging to capital G.
So the center will always have the identity.
Center will always have identity. So actually center will form a group, a subgroup of the full group, right? Yeah, which has an identity element, of course. It's a abelian group because it will, if it commutes with every element, it will also commute with an element of the center. It's going to be an abelian group. In SU2 case, you can show, with a little bit of work, you can show that if you take the center has two elements. One, this of course identity is 2 by 2 matrices, right? This is obviously belongs to SU2, but also there is an element which is -1, -1, 0, 0. There is also the unitary. This is unitary, and determinant equal to +1. Determinant is +1, right? Because it's a 2 by 2 matrix. Even dimensionality, right? The determinant doesn't change if you multiply with minus sign. So that's the center. So the center of so this is the center of SU2.
And SU2 is irreducible or reducible.
SU2 is what?
Irreducible or reducible, this representation.
No, it's not a representation. Sorry, it's not a. Yeah.
The representation by Cauchy matrices, is that reducible or irreducible?
Is irreducible.
Irreducible.
Lie algebra, yeah, it's irreducible.
So this is because the center has only the element proportional to identity by school.
Yeah, I mean, of course, this is a center, and yeah.
Because the center has only elements proportional to identity.
Yeah. You mean a discrete set of? This is a discrete set.
Yeah.
Yeah.
By school amount.
Yeah. And this, okay, although in this course we're not going to emphasize too much on that, but you can see, I mean, we will discuss it maybe a little bit later, that there are, so I mean, this is Z2 group. After all, this is a Z2 group, right? Because there are two elements, right? Square of that is this. That was the Z2 group. The Z2 group was generated by identity and say omega. So omega square with omega square equal to identity. Right? So this is exactly the Z2 group. And so this Z2 group, I mean, clearly the eigenvalues of, I mean, if I look at any eigenvalues, the omega can have only, eigenvalues can only be, so eigenvalues of omega in some representation. Okay. Eigenvalues of omega can be only plus or minus 1. Right? Because omega square is identity, and identity always has eigenvalue 1 in representation. So this can only be plus or minus 1. And then you can ask what kind of representations are plus 1 and what kind of representations are minus 1. It will turn out, and we will now discuss it tomorrow, that all the spin half integer spin representations will have minus 1. And all integer spins will have plus 1. Okay. So that is what happens. So if you think in terms of SO3, this again, you will see it more clearly in next time. I hope so. That even in SO3 case, I mean, after all, it's 3 dimensions. SO3 is a rotation group of 3 dimensions, right? You can also put fermions in the 3 dimension, right? I mean, usually when you talk about bosons, scalars or vectors and so on, they are all integer spin representations, right? They all have only integer spins. So on them, this center, this omega will act as a +1. But if you look at this fermions, if you put fermions, spinors, in 3 dimension, spin half, they will have a -1 eigenvalues. So it splits. The generalization of that, I mean, if you take SU3, for example, if you take SU3, you see, now it's a 3 by 3 matrices. You can take identity. Of course, identity is unitary and it satisfies everything. Okay. But you can also take, say, omega 0. I will define what omega is, not this omega. 0 omega 0, 0 0 omega, and omega square. Just replace omega by omega square. Where omega square is everything else 0. So where omega is a third root of unity. Okay. Well, you see that first of all, this has to be proportional to identity. Why? Because we are saying that they should commute with every element of the group. Okay. So that can only happen if it's proportional to identity for these groups. But then the only freedom is to put some number times identity. The proportional identity, but it has now here also condition determinant equal to +1, right? So determinant is omega cube, right? Omega cube should be 1. So omega is a third root of unity, e to the 2 pi r over 3. Right? So this exactly gives you a Z3 group. Remember at the beginning when we talked about the finite groups. So this is Z3 group. In general, if you go to SUN, you have a Zn group. And just like SU2, these representations were classified this integer spin or half integer spin, which had different eigenvalues for omega. Same way, for all of these Zn in SUN, the representations are classified in terms of the Zn action. There are different types of representations that happens. What we call fundamental, anti-fundamental. I think you were asking the question, right? The fundamental representation will come with, say, eigenvalue, for example, this. Then anti-fundamental will come with a minus sign, e to the with a square, omega square. So that differentiates them. Okay, so I think I took too much time, 2 hours almost. So we will meet tomorrow at 11. Right? There will be a tutor. I mean, we have not. The tutor is going to be an Iranian postdoc. Her name is Aida Zadeh. So she has kindly accepted to do the tutoring, but then she has to fix a precise timetable when she is free and when the room is available and so on. So hopefully there will be one by the end of this week.
Do we give the homeworks?
You will give it to homeworks to her, yeah. Maybe, I mean, once she fixes, maybe she can come here so that I can introduce you to her, and then maybe she can tell you. Maybe she prefers to have the homeworks in her mailbox, in which case you could just put in the mailbox. Okay. See you. See you tomorrow.
Should I put?
I think you should grab the last button.
Yeah.